In the vast theater of space, stars live, shine, and die. Most fade quietly. Some go out with a bang, and a rare few leave behind something stranger, something impossibly dense, something frozen in time, something that remembers the universe as it was billions of years ago. These are neutron stars, the remnants of collapsed giants. They're not just astronomical objects. They are cosmic time capsules. Each one is a frozen snapshot of a dying star, a record of extreme physics, ancient explosions, and the deep, buried memory of matter under unimaginable pressure. Today, we dive into one of the universe's most mysterious relics. We'll explore how neutron stars are born, what secrets they hold, and why they may be the most profound fossils in the cosmos. This is the story of neutron stars, dense, dead, and endlessly revealing. To understand a neutron star, we begin with a death. Not just any death, but the end of a massive star, at least 8 times the mass of our Sun. For millions of years, such a star burns hydrogen into helium, helium into carbon, and so on, layer by layer, until it builds a dense iron core. But iron is the end of the road. It cannot be fused into heavier elements without consuming more energy than it gives off. So the star collapses. In less than a second, gravity crushes the core. The outer layers rebound in a violent explosion, a supernova, blasting material into space and briefly outshining entire galaxies. But what's left behind doesn't disappear. If the core is just the right mass, not too small, not too big, it stabilizes into something new. A neutron star, a city-sized object with more mass than the Sun. A gravitational fortress where time slows, space twists, and matter behaves like nothing we know. Imagine a sphere just 20 kilometers wide. Now fill it with 1.4 times the mass of the Sun. The result? A neutron star, so dense that a single teaspoon of its material would weigh around 1 billion tons. Inside, atoms no longer exist in their familiar form. Electrons and protons have been squeezed together by gravity, forming a solid soup of neutrons, hence the name. The crust is a shell of superdense nuclei. Beneath that, an exotic mix of neutron-rich matter, possibly superfluids, hyperons, or even quark matter, stuff that only exists inside particle accelerators, or here. Neutron stars are nature's most extreme laboratories. They generate magnetic fields trillions of times stronger than Earth's. Some rotate hundreds of times per second. Pulsars, beaming radio waves with clock-like precision. But here's the real magic. A neutron star is frozen in its final form. It can't burn, can't fuse, can't change much. It simply persists, holding inside it the physics, composition, and memory of the star that died to create it. In 1967, a young astronomer named Jocelyn Bell Burnell noticed something odd in her radio data. A repeating pulse, like a heartbeat, every 1.3 seconds. At first, it was jokingly called LGM for Little Green Men. But it wasn't aliens. It was a pulsar, a rapidly spinning neutron star with magnetic poles that emit powerful beams of radiation. As it spins, those beams sweep across Earth like a lighthouse, producing regular, precise pulses. Some pulsars are so consistent, they rival atomic clocks. Over time, we've discovered thousands, each one a clock, a fossil, and a storyteller, ticking through cosmic history. Some spin hundreds of times per second. Some orbit other stars, even other neutron stars, allowing us to test Einstein's theory of general relativity in extreme environments. These pulsars don't just tell us about themselves. They help us measure gravitational waves, test the fabric of space-time, and even map the galaxy. Each one is a time capsule, and the more we study them, the more they tell us about how the universe works. Neutron stars don't change much after they form. They cool, they slow, but their core structure remains locked. That makes them fossils, frozen relics of ancient stars, some of which formed billions of years ago. We can analyze their mass, radius, and composition to reconstruct the supernova that formed them. Some even preserve clues about galactic history, where the first heavy elements came from, or how the Milky Way evolved over time. And if we're lucky, we can find neutron stars that are thousands of light years away, still emitting radio pulses, still ticking from an explosion that happened before humans ever walked the Earth. We study them not because they're exotic, but because they're familiar in a way we rarely see. They are record keepers, and they are everywhere. But what happens when time capsules meet? In 2017, two neutron stars spiraled into each other in a distant galaxy, an event we detected both in gravitational waves and invisible light. It was the first time humanity had watched two neutron stars collide. The result? A burst of radiation, a ripple through space-time, and the creation of heavy elements, gold, platinum, and uranium. That single collision produced more gold than Earth contains in its entirety. And it proved that neutron stars don't just remember the past. They create the future. These collisions are how the universe makes its heaviest elements. Each gold ring, each uranium atom, likely born in the heart of a dying star, or in the crash between two time capsules of cosmic memory. Inside a neutron star, physics is strange. Gravity is so strong that time itself runs slower. Matter behaves more like a quantum fluid than a solid. And we still don't fully understand what happens deep in the core. Some theorists suggest that deep inside, neutrons break down into quarks, a quark star, a form of matter never seen directly. Others propose layers of exotic phases, nuclear pasta, where nuclei arrange themselves into bizarre shapes with names like spaghetti and lasagna. And these aren't science fiction, they're testable. By measuring the mass and radius of neutron stars with instruments like NICER, LIGO, and the upcoming Einstein telescope, we begin to unlock what lies inside. Neutron stars give us access to physics we could never recreate on Earth. They're not just leftovers. They're natural laboratories, perfectly preserved. And every new discovery brings us closer to understanding the very building blocks of the cosmos. Around the galaxy, thousands, perhaps millions, of neutron stars drift in silence. Some spin, some pulse, others wait in darkness. We've only begun to map them. With every passing year, telescopes like FAST, CHIME, and SKA are detecting new pulsars, new signals, and new surprises, including fast radio bursts, which may also originate from magnetars, a special type of neutron star with magnetic fields beyond comprehension. Future missions will explore them in more detail. X-ray telescopes to measure their surfaces, gravitational wave observatories to detect collisions, deep sky surveys to catch the faintest whispers of ancient explosions. We are just scratching the surface, because these aren't just stars. They're time machines scattered across the galaxy, each one telling a different part of the story. Neutron stars are the universe's archivists. They do not evolve. They do not speak loudly, but they remember. Each one is a frozen memory of a massive star that once lived, burned bright, and died in fire. Of a galaxy that was younger, a universe that was still forming. And though they are silent, they are not still. Their pulses reach us across the void. Their collisions forge the elements of life. Their very existence challenges what we think we know about matter, time, and the edges of physical law. Neutron stars remind us that even in death, a star can illuminate the future. Even collapsed and cold, it can speak across space and time. And when we listen carefully, we hear not just the echoes of ancient explosions, but the quiet, ticking heartbeat of the universe itself.